Peace. So I've had this book for a while. It's called Quantum Physics in Minutes. The inner workings of our universe explained in an instant. I was watching another YouTube channel, and the woman who runs that channel, she had recommended this book. I bought it sometime last year, and I just decided that it might be a little fun to take it out and share some readings with you from it, a little bit here and there. A couple of years ago, when my second eldest son graduated Tufts University in physics, he got an undergraduate degree, major in physics and a minor in computer science. And I had him as a guest on my channel. His name is Jordan, and you can go through my archives and check out that video. And he went on to University of Chicago, where he was pursuing a PhD in quantum physics. I think he's since dropped the quantum part and just doing physics. I don't know anything about any of that. All I know is that the University of Chicago has an amazing library underneath this huge, this like ginormous glass dome. So I would love to go back and visit there. So I got this little book so I don't have to bug him, because when I try calling him on the phone to speak with him, he's like, "Mom, I'm busy." Busy doing what? I'm busy pursuing a PhD in physics. Don't have time to answer silly little questions. So let's read. What is quantum physics? Quantum physics describes the science of the very small things tinier than billionths of a meter on the scale of atoms, subatomic particles, and the wavelength of light. It also shows how many properties are quantized on these tiny scales, subdivided in discrete units, rather than being continuously varying quantities. In our everyday world, it's hard to imagine the properties found in this microscopic world. For example, there are particles like electrons that have no physical dimensions and others with no mass. Strangest of all, however, is the notion that particles can act like waves and waves can act like particles. This simple yet confounding fact lies at the heart of quantum physics and everything that subsequently flows from it. It took scientists a long time to accept the bizarre idea, and the revolution that followed had a profound effect on modern science. Yet the discovery of quantum theory had its roots in a much older debate, the centuries-long argument over whether light is made from particles or waves. Anyone who is not shocked by quantum theory has not understood it. Attributed to Niels Bohr. Is light a wave? Quantum theory has its roots in a fierce and long-running debate over the nature of light. The question as to whether light is made from particles or waves dominated science in the late 17th century. In 1678, Dutch scientist Christian Huygens popularized the hypothesis that light propagated in the form of a wave based on earlier ideas of philosopher René Descartes. Of course, waves ranging from tidal waves in water to sound waves in air need a medium through which to propagate. It was clear that light waves were not using air as a medium. Space was known to be airless, and yet we can still see the light of the sun, stars, and planets. To get around this, Huygens hypothesized a medium that he called luminiferous ether. He neglected to explain exactly what this ether was, beyond it being weightless, invisible, apparently everywhere. Unsurprisingly, many scientists, key among them Isaac Newton, I guess that would be Sir Isaac Newton, were unconvinced by Huygens' wave theory. Instead, they argued that light must be made from particles. Is light a particle? Influential English physicist Sir Isaac Newton proposed a model of light as discrete particles, so-called corpuscles. It was based not only on objections to the wave theory of Huygens, and I'm sure I'm probably pronouncing that Dutch name incorrectly, but bear with me, but also upon observation. Newton pointed to the way in which light is reflected from a mirror. Waves do not travel in the straight lines needed to create a reflection, but particles do. Furthermore, Newton explained refraction, the bending of light in certain materials such as water, as the effect of a medium attracting particles of light and speeding them up. Finally, step outside on a sunny day and you will see that there are sharp edges to your shadow. Whereas if sunlight were made of waves, your shadow would surely be fuzzy. Newton's model became the leading theory of light, but it wasn't well received by everybody, and his rival, Robert Hooke, was one influential voice who still favored the wave theory. Then, in 1801, long after Newton's death, the double slit experiment seemed to disprove corpuscles once and for all. So, how many of you have heard of the double slit experiment? Newton erroneously used the refraction of light passing through a prism to argue for its particle, like nature, but his discovery that white light can be split into many colors still led to the important breakthroughs, including the entire field of spectroscopy. And it also ended up on the album cover for Pink Floyd. So there you have it. So I'm going to leave you there for now. And, oh, wait a minute. There's the double slit experiment. You know what? I'm going to go ahead and read that one, and then I'll wrap this up because I might as well. We went through quantum physics, then we went through is light waves or is light particles. And so we have to clarify it, clear it up with the double slit experiment. And for those who have just joined us, I'm reading from Quantum Physics in Minutes, the inner workings of our universe explained in an instant, and I'm on page 14, and we have learned so much. Ready for my undergraduate degree in physics. The double slit experiment. Despite the success of Isaac Newton's corpuscular theory of light, the rival wave theory retained some proponents, and at the beginning of the 19th century, Englishman Thomas Young appeared to disprove Newton with an experiment that is replicated by high school students to this day. Young's experiment involves shining sunlight through a barrier containing two thin slits and onto a screen. Once through the slits, the light creates two spreading of diffraction patterns, which begin to overlap and interfere with one another. Where a trough in one wave coincides with the peak of another, it causes them to cancel out, so that when the light finally reaches the screen, the canceled waves leave dark bands known as interference fringes. Since only waves can interfere in this fashion, Young concluded that light must be made from waves. By studying how the different colors within sunlight formed different fringe patterns, he was then able to estimate the wavelengths of the various colors. Interesting. I always wondered how they came up with the wavelength, and now we know. So there you have it. So do yourself a favor and Google the double slit experiment so you can see the image. And there we have it. So we're going to end here for tonight on page 15 of Quantum Physics in Minutes. So have a good evening, and I will catch you guys later. Thanks for joining.